if you have any questions, we'll have a brief Q&A session after the talk. And of course, you can also use the raise hand feature, and after the talk, we'll be happy to let you ask your questions also live if the time allows. We have 4 exciting talks today in our stream-based monitoring session, and we'll start in a minute. And our first talk will be on given by Maximilian Schwenger on verified Rust monitors for LoLa specification. And you can start the video in 10 seconds or so. Thank you. Are we having some difficulties?
Welcome to my presentation, Verified Rust Monitors for LoLa Specifications. The quintessence of my talk is an age-old question supposedly posed by Juvenal in 100 to 200 AD. And the question is, quis custodiet ipsos custodes, which roughly translates to who watches the watchman. And this question is particularly interesting for runtime monitoring, because here we know we have a system which we cannot trust. So we employ a monitor, and this monitor observes the system and tells us, hey, is everything going according to plan or is something going wrong? Now, since we know we can't trust the system itself, why would we want to trust a monitor? So our goal here is to verify the monitor. This is something we cannot do for the system itself, because the system is highly complex. And in comparison, the monitor is rather simple, so here verification methods do actually scale. Now we usually get the monitor based on a specification. In our case, this is a LoLa specification. And this specification is somehow translated into executable software or hardware. Now what we do instead is we introduce an intermediate step where we translate the specification into code, in this case Rust code. And we have full control over this compilation. So what we can do is we can automatically inject annotations in the code, and these annotations should help us in the verification process. So for the verification, we use Viper, and Viper translates these annotations into an SMT model, and this model is passed to the SMT solvers D3, which verifies whether the model is correct or not. And if Viper gives us a green light, then we know our code is correct, and also is our executable correct. This idea is not entirely new. For example, the Copilot framework did something similar, where they translated their specification into C code and used a bound model checker to verify the correctness of the code up to a certain bound. In our approach, however, we don't have this bound, so we fully verify the code. To understand the whole process here, we have to start by understanding what the specification looks like. So let me give you a brief introduction into the stream-based monitoring language LoLa. In LoLa, we have input streams, we have output streams, and we have triggers. Input streams represent consecutive readings of sensors within the system, and outputs kind of refine the values we get from the system. For this, the outputs access different values, either from other output streams or from inputs, and compute new values, and trigger conditions at the end take these output values and check some properties for that. These checks are always binary, so at the end we know either everything is fine or something is going wrong. This information is then passed on to the CPS again. In a concrete example, we take this specification here as a running example for the talk. We assume the system has only one input, and this is an altimeter, giving us values for the altitude that is measured right now. And we check whether the altitude of the system is over a certain bound for 3 consecutive readings. So for this, in the too high output stream, we access the current next value of the altimeter. Here, when evaluating the specification, we can see that there are 3 kinds of accesses to the altitude stream. One with -1, one with +1, and one with 0 as an offset. And for these past and future offsets, we know that this works most of the time. However, in the first and last iteration of the monitor, these accesses will fail. Because in the first iteration, there is no previous value, and in the last iteration, there is no next value. So in these cases, we have to supply a default value and substitute it for the actual altitude. In the other axis, however, we know that this will never fail because we access the current value of the altimeter, and we only compute the too high output stream if we get a new reading from the altitude, so we know these accesses will never fail. Now, when having a look at the illustration to the left, we can see that there are kind of 3 phases. We have a prefix phase in which past accesses might fail, or will definitely fail. We can decide this statically. And we have a postfix phase where future offsets will definitely fail. In the middle, in the monitor loop, we know that all of these accesses will succeed. So we can treat this somehow differently. When translating the specification into code, we will get different code for the prefix, postfix, and monitor loop, and we have to show that all of these implementations are correct. However, we want to improve the generated code a little bit to make it more performant as well. And we know that these optimizations will be correct because we prove the correctness of the monitor at the end. Now, in our translation for the prefix, we know that we want to evaluate the output stream, so we access the 3 values of the altimeter. But we know that the last value of altitude is not there. So rather than having a conditional checking whether the value is there dynamically and then substituting the default, we can already do this statically. So rather than accessing memory here, we replace the memory access by 0. And in this particular example, this allows us to just remove the whole expression here because it boils down to false. In the monitor loop itself, we still have memory accesses, but we don't need conditionals as well because we know these values will be there. So we can just access the memory rather than dynamically checking whether the value is here. And in the postfix, it's pretty much the same situation as in the prefix. So when accessing future values, we can instead replace this by the default value and just, in this case, remove the expression. And these optimizations here have 2 major impacts. First of all, we eradicate most conditionals. And second, some memory accesses become constants instead. And we know that memory accesses and conditionals both are fairly expensive in actual executable code. So we wanted to see how strong are these performance benefits at the end. So we compared it against an interpreter for Lola, which was presented at CAF 19. And for our simple running example, the interpreter needed around 430 nanoseconds per event, whereas our compilation only needed 6 nanoseconds, which is 1.4% of the running time. We also tried a more involved specification for network monitoring, and we can see that it's much more complicated because the interpreter needed 1.5 microseconds per event, and our compilation also needed longer, but it only needed around 60 odd nanoseconds, which is 4% of the running time of the interpreter. So we know what we generate is highly performant code. But the best code doesn't really help us if it's not verified. So let's have a look at how we verify the whole thing. And the grand challenge here is that in Lola, we argue about streams. and a stream is an infinite sequence of values. Whereas in Rust, we only have finite memory, so we have a finite excerpt of the stream to work with. In previous work, it was already shown that this finite excerpt can suffice, but we want to show that our implementation actually is correct and this does work out for us. Now to show this, we introduce an intermediate layer between Lua and Rust, which is ghost memory. And this ghost memory is only used during the verification and not during the actual execution. And here we have to show two things. The first thing we have to show is that the memory in Rust is the same as the one we have in our ghost memory, at least the values we have access to in Rust. And the second thing is we have to show that each value we add to the ghost memory is the same as the one that should be there according to the theoretical Lola model. So these are the two things we have to show. And we do this by injecting the appropriate annotations into the code. The most interesting part of these annotations are the invariants for the while loop, the monitor loop. And here you can see the first invariant has a universal quantification over an I, and I ranges over the range of 0 to mu of A, so the memory consumption of the stream A. And this essentially allows us to iterate over all values that occur in this finite excerpt here, down here. Now for each of these values in this finite excerpt, we show that the memory, that is the memory we have access to in Rust, is the same as the value in the ghost memory. So this is the first thing we show, and this allows us to prove that the values down here are the same as the ones over here. For the second part of the proof, we have an additional invariant, and this invariant equates two things. On the left-hand side, we have the value new to high, which is the value that was computed in the Rust code based on the memory in Rust. So these are all values that are actually physically present. And this value is compared against the evaluation of the expression from the spec only based on the ghost memory rather than the real memory in Rust. So we can see here that we access the respective values of the ghost memory. And if these two computations are correct, then we know that the values here in the ghost memory, each of them is the same as the one we would have gotten if we evaluated in theoretical Lola. And in combination, we know that every value we compute in Rust is the same as the one we would have gotten in Lola. So all trigger responses are correct. And that's essentially what we wanted to show. Now this is all nice and well in theory. We wanted to see whether this technique actually scales up for real specifications. So we ran a couple of experiments. The first experiment was with our running example here, the simple spec with the altitude. And trying to verify this revealed that we needed around 200 seconds for the verification and around 700 megabytes of memory, which is reasonable. But the specification is rather simple, so we wanted to see how well it scales. So we went and took the network specification and we tried to verify it again, and it worked out. So here we can see that the consumption, the resource consumption is significantly higher, of course, because the specification is more involved. But it was still around 1000 seconds and around 3 gigs of memory. So this is really well. And lastly, we tried a different specification, which is a fly phase detection specification for autonomous drones. And when trying to verify the implementation, we got a couple of errors. So Viper reported that there might be arithmetic problems in the implementation. Upon further inspection, we found out that the specification had implicit assumptions on the inputs, namely that the time input stream had monotonically increasing values. And this implicit assumption might be violated dynamically. And if this is the case, then the monitor would just fail and crash. And it's unclear how the system would react in this situation. So this is a major problem, and we detected this with the verification. So we were able to detect an implicit assumption on the input streams. This was quite amazing. Now we corrected these implicit assumptions and added a check so that we no longer can divide over values that are 0. And for the corrected specification, we tried the verification again, and it worked out. We needed around 6 to 16 minutes and around 1.5 gigabytes of memory. However, out of the 20 runs we conducted, 2 of them timed out and 4 failed. And failing here means that either the C3 crashed internally or Viper crashed internally. Or even Viper reported that some assumptions could not be verified. And this is curious because we did not change the specification between runs. And still, sometimes it just was able to verify it, and sometimes it reported that some parts are not verifiable. So what this really shows us is that we rely on external tools. And while these tools are really amazing, sometimes they have problems, they are not perfect, and every improvement on these tools will also benefit our approach here. So for the approach itself, the main takeaway here is that we successfully detected specification errors that would lead the monitor to crash in the actual execution. And we were able to verify even relatively complex specifications. So the monitors were relatively complex specifications. And this is really a positive result that tells us that we should go on in this direction. And this is something we want to improve on in the future and see what's still possible here. Now, in conclusion, we asked the question of quis custodiet ipsos custodes, who watches the watchman? And the answer is, in this case, well, Viper does. And Viper was able to successfully verify interesting specifications or monitors for interesting specifications. And the code we generated was highly performant. So that's a really positive result for us. If you want to find out more about the whole thing, you can go to GitHub. There is the fully compiled code for these specifications I mentioned. Just look for the Lola2 Rust artifact. And in the paper, there's also more information on the specification analysis and concurrent implementations for the evaluation of the monitor. And now I'm happy to take any questions you have.
Thank you, Maximilian, for this nice presentation. All right, we have time for a couple of questions.
So I have a question, Klaus Havelund here.
Hi, Klaus. Go ahead.
Hi. Yeah, so this is not so much about your tool, but more the choice of focusing on Rust. So did you experience any problems with working with Rust? So Rust clearly has some advantages for embedded programming, systems programming, but I have found it to be a royal pain in the neck to program in. Is that something you have experienced?
Yeah, it's quite interesting because Rust is kind of a double-edged sword here. I think the development time, the time you need to get your code running is higher than for other languages, but the debugging time in our experience is significantly lower. So I think you have to get around the borrow checker and the type checker. But as soon as you have reached a point in experience that you really can work with the help the compiler gives you, then in our experience, it's quite helpful to use the language. So we are now at a point where we are quite comfortable with the language, and then it's just helpful.
Yeah, thanks.
Sure.
All right, thank you. There's a question from Dimitri. Please go ahead and unmute yourself, Dimitri.
Yes, hi. Thanks for the talk. I didn't quite get how you connect what Viper actually proves to the semantics of Lola. In the semantics of Lola, you have these constructs that access the stream at different offsets, and I would have expected to see this in some of the assertions that you generate. Is this the case, and you just didn't show those? Or?
Right. There's a variety of different assertions in the code that are needed to just, for bookkeeping more or less, to see that all accesses are correct and the values are never changed unless we want them to change. I skipped over all of them. You could find more details on GitHub on the compiled version or in the paper. But generally, the most interesting part or the most yeah, exciting part is what I showed you, the invariance. And even there are a couple of more assertions that just make sure that the computation with respect to the ghost memory is the same as the one we get in the actual implementation. So the actual realization, which is executed in code.
Thanks.
Sure.
Very quick question, Maximilian, before we conclude. So the semantic model you're assuming is that you're saying the monitor compilation is correct when the produced values are the same, right? As the interpreted version. How would that change if you just are interested about the values of the triggers?
It would change in some way. So we could have more optimizations by just ignoring the output computation. Sometimes you don't need outputs, or you can inline them, and you get the same result with respect to triggers. We did not consider this in this work. There's another talk later on in the session where we talk more about this for RT-Lola. Here, it was really correctness with respect to all streams, input, output, and triggers.
All right, thank you very much.
Sure. You're muted, Hasan.
Oh, sorry, I was muted. My bad. So the next talk will be given by Felipe Corostiaga, and it's about unifying the time event spectrum for stream runtime verification.
Hello, I'm Felipe, and I am one of the authors of the paper Unifying the Time Event Spectrum for Stream Runtime Verification, in which we compare two languages for stream runtime verification, one of which works with synchronous streams and the other one works with asynchronous streams. So let's begin with defining what we mean with synchronous and asynchronous streams. So asynchronous streams for us is essentially a sequence of values, one of which is active or in focus, and we call it now. And here we have the ability to refer to different instants by their distance to the current time. So for example, we can refer to the instant Q5 as Q plus 1, and Q2 as Q minus 2, because the current instant in the picture is the fifth instant with index 4. We use the language Lola to define streams in this synchronous realm. On the other hand, an asynchronous stream is a timestamped sequence of values, and we have the notion of a current time which might not coincide with any event in these streams, and we can no longer refer to instants by their distance to the current time. Instead, we jump around over events, and we can refer, for example, to the event S right after T, or to the event at R before the last event of R with respect to T. And we use the language Striver to define streams in this realm. So essentially what we do in this paper is showing that we can translate a property in the synchronous realm to a property in the asynchronous realm, which is equivalent, and vice versa. Graphically, this means that we can take a specification in the synchronous realm. This is a Lola specification. Apply a function to the specification, which we call Striver, and get a Striver specification. We can translate the input synchronous streams to asynchronous input streams using the toStream function shown on the left of the picture. We can compute both specifications with their corresponding engine and obtain equivalent sets of output streams, synchronous and asynchronous. And the other way is analogous. It says that we can take a Striver specification, apply a function Lola to it to obtain a Lola specification, and we can translate the input asynchronous streams to input synchronous streams using the toSec function, compute on both sides, and obtain equivalent sets of synchronous and asynchronous streams. So let's try to translate a Lola specification to a striver specification. If we have a Lola specification like this, phi, and we apply the function striver to obtain a striver specification, what we get is this specification, and the original specification in Lola, if we check the dependency between the instants, we will see that the value of s at 0 at now depends on the value of r at 1, which depends on s at -1, which depends on r at 0, and so on and so forth, until we reach the base case of r at -1, which would depend on s at -3, but it doesn't exist. It falls off the trace, and thus it uses the value at that point of r. This is r at -1. The value of that instant is 7. In striver, what we get is the same picture. So if we want to compute the dependency of r at t, we would see that it depends on s, on the value of the event of s before the last event of s, and that event itself depends on the next value of r, and everything is alright. But the problem is that in striver we cannot, since the streams are asynchronous, we cannot count on the presence of r at that point, and it cannot exist. And if it doesn't exist, the value of the event of s at that point depends on that event in r, and we end up with a circular dependency, which is something to avoid because it renders the specification not well defined. The problem here is that in the dependency graph of the original Lola specification, we do not have a walk of weight 0. This is, in this graph, we cannot have a sequence of edges whose weight is 0. Instead, in striver, which means that the Lola specification is well defined. Instead, in the translated striver specification, what we have is that r depends on past values of s, and s depends on future values of r. But this specification is not well defined. It does not guarantee the absence of circular dependencies between the events, and in consequence, the translated striver specification is illegal. To tackle this problem, what we do is translating the Lola specification to an equivalent Lola specification using our custom function expand, which essentially gets rid of cycles with edges of mixed weights. In this case, it inlines the definition of R into the definition of S, and we end up with a dependency graph, which, when we translate the Lola specification, the expanded Lola specification, we get a valid, a legal striver specification. So the steps are that we take a Lola specification, we expand it to get rid of the cycles with mixed edges, and then we translate the resulting Lola specification to striver. In lemma 2 in our paper, we show that this can always be done for any Lola specification. And in theorem 1 in our paper, we essentially show that this diagram is correct. So we can take a Lola specification, we can expand it, or we can assume for lemma 2 that it does not have cycles with edges of mixed weights, and we can always obtain a striver, a legal striver specification from it. We can translate the input streams, compute on both sides, and obtain equivalent output streams. Now, to translate from Striver to Lola, there's something else, because we know that we will end up with two streams R and S with some values, but we also need to capture the timestamps of the events, of the asynchronous events. So we need an extra synchronous stream, which we call time. And now the question is, which values we include in this stream? So what we can do is take as the values of time the timestamps of the events in R and S in this case, which are these. And we simply fill the squares of R1 and S1 with the corresponding values. And we fill the blank spaces with a fresh constant, which we call notick, and represents the absence of values. In this case, graphically, they represent the absence of circles in the diagram at the top left. Instead of writing notick, we simply write bottom, which represents exactly the same. But this is not the only election for the stream time. Alternatively, we could have chosen the sequence of times with a very small step that ensures that all the timestamps of the events in R and S are captured, are present. So we take, for example, the step of 0.1, and we use that as our stream time. We fill the corresponding squares, and we fill the blank spaces with notick. What we end up having is instant of this kind, at which we have a value at time, but no value in these streams R and S original. And we call this void instance, and the presence of this void instance represent or hint the computation that was actually unnecessary to be done, and thus it was not the best choice and it was inefficient. As a third alternative, we can choose something intermediate with not only those the timestamps of the events in R and S, but also a few of these void instants, but which is still more efficient than choosing the whole time domain as the sequence time. We call this alternative the temporal backbones, and we say that the temporal backbone is covering if it contains all the events in evaluation, of all the events in the original streams of evaluation, in this case of R and S. So any covering temporal backbone in our example will be a superset of time 1. In a Striver specification, not only do we have to say the value of the streams, but also the times at which it will generate events. In this case, we are saying that the stream R will produce a value whenever S produces a value, and the value it produces is the last value of S, or 7 if there is no such previous value. So, in the Lola specification, we represent this as saying, so if S is not ticking right now, then we are not ticking either. Otherwise, we take the last value of S, and if it doesn't exist, if it falls off the trace, we use 7 as the default value. And we show in the paper in theorem 2 that if you choose a covering backbone for evaluation and apply and use it to translate the input streams, and translate this driver specification using the Lola function, you end up with equivalent output streams or equivalent sets of output streams. We have programmed both Lola and Striver using Haskell. We call them HLola and HStriver, and set up a couple of experiments of properties over a dataset which is available online, which is called Orange for Home, and contains data of an instrumented house in a time span of 25 days. And we compare the efficiency of Lola and Striver using Lola with different backbones. And these are the results. We can see here in brown that Lola with an inefficient backbone, this is a backbone that results in many void instances, is much more inefficient than a Lola with less void instance and than the corresponding Striver specification. So, in summary, what we have done is studying synchronous and asynchronous stream runtime verification. We have shown that their expressivity are the same, in particular using the language Lola for synchronous stream runtime verification and Striver for asynchronous stream runtime verification. We show that every Lola specification can be translated to Striver, and we have shown that to translate from Striver to Lola, we need to choose a temporal backbone. And we show some alternatives, for example, using the full domain, the full temporal domain as the backbone, or we can use only the input event timestamps as the backbones, or we can use the input event timestamps and some points that we know are those points where some stream might be producing a value. And we show that the choice of the full domain is always covering, because you cannot leave anything out, but it's much more inefficient than being a bit smarter and choosing a backbone that contains many less void instances. And also we have assessed these results with an empirical evaluation using the dataset Orange for Home. And this is it. Thank you for your attention, and we are now open for questions.
Thank you, Felipe, for this nice presentation. And as Felipe said, the floor is open for questions. All right. I have one before maybe other questions come. Felipe, can you hear me?
Yes, I can.
So maybe I missed this point just in your presentation. When you say that you're translating Striver specifications into Lola specifications, right? Then well, you're using an additional stream for looking at the timestamps. But in my understanding, if you don't know how many inputs will arrive in a certain time period, right? So how do you accommodate that? How does the Lola specification look that has to accommodate for this unknown number of possible inputs using just offset expressions?
Well, the idea is that you actually pre-process the input events that you fed into Striver for the. Okay, so there are two settings. If the only points in time when you have to produce an event are those of the input stream events, say, then you don't have to make room for anything, right? I mean, you only have to produce a value at each input event.
Yes, sure. I mean, you're saying you just have to accommodate for the arrival of each input and then transform that to Lola. But I was thinking maybe this was not part of the talk, but are you also considering Striver specifications that do aggregations?
You mean aggregations over windows?
Yeah, over Windows.
No, those
I
are not considered. No.
Okay, thank you. Any other questions from the audience? Let me just look if there's any questions on Slack. All right. If you have any other questions, please use the Slack platform, and Felipe will be happy to answer your questions also after the session or during the talk. All right, thank you. So we're going to move to the next presentation, and the next presentation will be about a benchmark generator for online first order monitoring. And the presenter of this talk is Srdjan Krstić.
Hello. My name is Srdjan Krstić, and I will be presenting this benchmark paper, which was co-authored with Joshua Schneider. Benchmarks are typically designed to evaluate execution time and memory usage of programs. Monitoring benchmarks have the same goal, and they consist of particular monitoring inputs, like the specification and the stream or a trace. Benchmarks are very useful. They allow us to analyze how particular inputs impact the execution time and memory usage of a monitor. They are also very useful to compare different monitors in a reproducible manner. When a benchmark also includes expected monitoring output, then it becomes a test case. And then we can use it to assess the correctness of the benchmark monitor. In this paper, we propose a benchmark generator designed to benchmark online first order monitors. The benchmark assesses performance by generating streams with characteristics tailored for a family of specifications that consist of temporal three-way conjunctions. The benchmark can also assess the correctness by providing a verified monitor as an oracle for the expected output. In this case, any monitorable metric first order dynamic logic formula can be used as a specification input of the monitor. In the rest of the talk, I will briefly explain three main components of the benchmark generator, which are stream generator, stream replier, and the monitoring oracle. I will exemplify their usage through use cases, which will be the correctness use case, showing how you can attest correctness of a monitor, and the performance use case, showing how to attest performance of a monitor. There will be a lot of demonstrations throughout this talk, and I hope this will make it exciting. Finally, I will summarize some successful applications of our benchmark in the past. Let's start with the first component, the stream generator. It has two modes of operation. It can generate a stream for arbitrary specifications, which is the first mode. And in this case, the specification does not influence the way the stream is being generated, other than the event type that will be in the stream. The other mode creates streams which are tailored for the previously mentioned temporal three-way conjunction. Stream characteristics are always provided as input to the generator, but then depending on the mode, it is either the event signature or a specific three-way conjunction. The output of the stream generator is a stream or a trace. Let's consider mode 1. It is intended for differential testing of monitors against our oracle component, which I will introduce shortly. In this case, the user must provide a signature, which defines predicates used in the specification and the events that will occur in the generated streams. For example, this signature shown on the slide defines two events, login and logout, each with two parameters, IP and port. How are these events generated? Well, the event names are sampled randomly and independently, while parameter values are sampled in two ways. With a configurable probability R, they are sampled uniformly from a large domain. Otherwise, they are uniformly sampled from a cache of most recently used parameter values. This ensures that the events have common parameter values and creates streams that are more challenging to monitor. Let's consider an example. Here is a signature that we just mentioned. Let's now use the generator with this signature to generate a trace. This trace will have event rate 2 and the time span 5. As you can see, the format of the trace is a CSV format, which is used in the RV competitions previously. It has 10 lines. Each line represents an event. Event names are shown in the first column, so log in or log out, then the time points, then timestamps, and then the two remaining columns are the parameters of the events. Event rate 2 means that there are two events with the same timestamp. And the time span means that there are 5 unique timestamps in the trace. Let's consider the second mode. Here, the idea is to force the monitor to evaluate conjunctions with a particular form, the form shown on the slide. And these actually have variable occurrence patterns that are configurable. Know that computing conjunctions or joins is a core operation in first-order monitoring. Hence, we specialized our benchmark generator for this particular case in order to assess the performance of this very important operation. As I mentioned, variable occurrence patterns are configurable. With some built-in patterns, like star, where one variable occurs in all 3 predicates, or triangle, where each variable occurs in 2 predicates. We make this conjunction a bit more complex by adding temporal operators. So namely, predicate A is considered in the past W time units, while the absence of predicate C is considered in the future W time units. Besides this W, which is also the parameter of our stream generator, there are other customizations, like frequencies of events A, B, and C can be configured, as well as the violation frequency that is expected to be generated in the trace for this formula, as well as specifying a particular parameter value that will occur much more frequently, which we call heavy hitter. Since our benchmark is for online monitors, we need to provide a component that will generate real-time streams. This component is the stream replier. The replier takes a stream or a trace and reproduces it in real time based on the timestamps that are in the stream. It can accelerate or decelerate streams based on a configurable parameter. It can also simulate out-of-order streams or convert formats and do many other things. Let's consider an example. Consider the star formula that I mentioned before. As you can see here, the variable occurrence patterns follow a star pattern. So the W variable, free variable, occurs in each predicate, while X, Y, and Z occur only in one predicate each. Let's generate a trace which is tailored for this specification by specifying -S as the flag. Let's use event rate 1, and let's say that there are 10 events. If we would replay this trace, it would take exactly 10 seconds to do it, because each timestamp increases by 1, and the time span is 10 seconds. But now we can modify this. We can accelerate the reproduction of this trace by 5, which would then reproduce this trace in 2 seconds. Finally, the third component is the monitoring oracle. It provides the expected output given the specification and the stream or a trace. The output is a reference verdict, which consists of all violations of the specification. A violation is simply a tuple which contains a time point where the violation occurred, the timestamp which this time point contains, and values of free variables when assigned violate the specification. The oracle is implemented by a monitor called Verimon++, which is a correct by design monitor. So let's consider the same formula as before, the star formula. And let's generate now a longer trace. Let's generate a trace which has event rate 5 and has time span 20. Let's reply it as fast as possible, which is acceleration -1 in this case. Let's convert it to a Verimon format, which is a format that our oracle reads. And then let's invoke our oracle to monitor the star formula. Once the oracle is done, we see that there were no violations, but we can modify the generation such that we force some violations. So let's increase the violation frequency to 0.4. Now we will actually see some violations. Let's now invoke the same trace, but with a different monitor, with a monitor called MonPoly. As you can see, the monitor also provides the same verdicts, which is a good correctness use case. We can now compare what the oracle says with the monitor that is being benchmarked and attest its correctness. Now let's see how we can attest performance. Let's generate a large trace. Let's generate a trace with event rate 40 and time span 1000. This trace will have 40,000 events. As you can see, the events have parameters which are sampled uniformly. Let's monitor this trace. Let's use mompoly. Mompoly is pretty fast and it almost immediately returns one violation. But what would happen if we would modify this trace a bit? So if we would generate these parameters using a different distribution. So let's use a zip distribution, and let's generate all parameters related to the free variable w in the formula using a zip distribution with exponent 5. Now you see again a trace with the same amount of events, so 40,000 events, but now just the parameters are sampled from a different distribution. So you can see that, for instance, parameter value 1 repeats quite often, and parameter value 1,000,001 also repeats quite often. So what would happen if we would monitor this with mompoly? It finds some violations, but it still did not finish. And as you can see, it takes much more time. So this is an example of how you can attest performance of your monitor and check how your monitor reacts to different distributions of parameters. Now let me summarize our benchmark's previous usage. It assessed scalability of parallel online monitor. It also showed impact of stream characteristics, time-varying stream characteristics, and out-of-order events on the monitoring performance. It also assessed correctness of first-order monitors, specifically mompoly and déjà vu, and successfully found bugs and semantical differences in these tools. In summary, benchmarks are important tools for assessing correctness and performance of monitors. In order to support further research in algorithms for online first-order monitors and facilitate reproducible comparison of the state-of-the-art, we propose a benchmark generator. It consists of 3 components: the stream generator, stream replier, and the monitoring oracle, and it is able to assess both correctness and performance of online first-order monitors. I thank you for your attention, and I'm looking forward to your questions.
Thank you, Sergeant, for this nice presentation. But I see Joshua is online, or oh no, there's Sergeant. Hi.
I'm here.
All right, the floor is open for questions. So there's a question from Doron Pellet. Now I'm interested to know about bugs, in particular if you found them in déjà vu.
Yes, we found, well, we call them semantical differences, well, or at least these outputs that were not initially expected from us and from what the oracle said. And these were mostly, I guess, one formula. I cannot recall the formulas exactly, but for instance, the definition of the active domain would not include the constants that were in the formula, which was something that was just not expected by the semantics of the oracle, and that this was the inconsistency. And the other one, I guess, when using arithmetic operations where you use equality, there was a sort of an implicit change of the quantifiers into quantifiers that go over active domain rather than over an infinite domain. So this was also unexpected.
Yeah, but this is documented. It should happen, right?
Yeah. Well, it was just not expected based on the oracles. Okay. That's why we say semantical differences. It was not a bug.
All right. Thanks.
I have also one question. So up till now, if I understand things correctly, the traces or streams are generated either randomly or by defining some pattern in which they should be generated. Mm-hmm. Let's say you figure out that in certain systems, certain traces result in many errors. Can you direct the search to patterns that focus on these specific errors?
Not really. These are, random traces. So I think the better way to discover bugs would be to sort of find good policies. I mean, if you want to find bugs in monitors in particular, then so find good policies to check. And traces are more for performance reason, for performance evaluation, I would say. So these are not, it's not smart enough to do something as, let's say, as you suggest. So.
Okay, all right. Thank you very much. We're moving to the final talk of the session. The final talk is on automatic optimizations for stream-based specification languages, and it's presented by Bernd Finkbeiner.
Hi everyone, this talk is about automatic optimizations for stream-based monitoring languages. My name is Bernd Finkbeiner. This is joint work with Jan Baumeister, Mathis Kruse, and Maximilian Schwenger. Now, one of the key motivations for this work is that monitors are often used in safety-critical applications. For such applications, we tend to emphasize having the most understandable rather than necessarily the most efficient code. At the same time, however, monitors work in real time and are often used on restricted hardware, so we definitely also need the code to be efficient. Now, optimizations are a way to bridge this gap. We're interested in transformations that improve the performance of the monitor, obviously without changing the outcome of the monitoring. For a stream-based monitoring language, this means that the behavior of the trigger condition must stay the same, but the behavior of internal streams can change arbitrarily. This gives us actually quite a bit of freedom. Code optimization is of course a classic research topic in programming languages. In monitoring, there has been surprisingly little work on this. So what we do in this paper is we introduce the first transformations for the stream-based monitoring language RT-Lola. Our two main transformations are the pacing type refinement, which statically eliminates unnecessary computations, and the filter refinement, which does this dynamically. The result is a whopping threefold speedup. But before we get into this, let me introduce our little running example. One of the main application areas for RT-Lola has been the monitoring of unmanned aircraft. If you're interested in this, you can find more details about this in our recent CAF paper. For the purposes of this talk, I'll just use a really simple example. We're monitoring the velocity and the acceleration of a drone. Let's say that the rule is that if the drone is already pretty fast, that is, it goes by more than 10 meters per second, then the acceleration should be limited to 1 meter per square second. Otherwise, we'll allow 1.5 meters per square second. Now, in Lola, velocity and acceleration are input streams. The rule about the maximal allowed acceleration is expressed as the trigger condition that you see in the last line. There is an if statement that uses either acceleration check 1 if the velocity is below 10, or acceleration check 2 otherwise. Acceleration check 1 and 2 are two internal streams, which then check whether the acceleration is below 1 or below 1.5 respectively. RT-Lola has a formal semantics which regulates precisely at which point in time these streams are to be extended. Each stream has a condition which is called the pacing type, which specifies how events on this stream are triggered. First of all, velocity and acceleration are input streams. They are extended whenever new data comes in, which can be at any time. Different input streams can be asynchronous to each other, so there's no need for them to be extended at the same points in time. Velocity and acceleration are each their own pacing type. Now, acceleration check 1 depends only on acceleration. Its pacing type is therefore also acceleration. Acceleration check 1 is computed whenever a new acceleration value comes in. The same thing holds for acceleration check 2. Now, the trigger condition actually depends on both velocity and on acceleration. Its pacing type is therefore the conjunction of velocity and acceleration. This means that the trigger condition is evaluated when we have both a velocity and an acceleration value available. Now, when we look at the overall picture here, then we see that it's not actually the case that all computations contribute to the trigger value. The computations marked in red are definitely unnecessary. What's the problem? The pacing types of acceleration checks 1 and 2 say that these streams are to be evaluated whenever a new acceleration value comes in. They are, however, only needed when the trigger condition needs them. That is, when the trigger condition sees that there's both an acceleration and a velocity value. Now, our first optimization, the pacing type refinement, fixes this by changing the pacing type. We strengthen the pacing type of the acceleration checks with the pacing type of the trigger condition. Now that we change the pacing type of acceleration check 1 and 2 also to the conjunction of velocity and acceleration, we make sure that these streams are only computed when actually needed for the trigger condition. Syntactically, this results in an explicit pacing type declaration. Both acceleration check 1 and acceleration check 2 now have this explicit declaration, velocity and acceleration. So this looks pretty good already. A lot of unnecessary computations have disappeared. However, if we take a closer look at the remaining computations, then we see that there is still some unnecessary work going on. Whenever the trigger condition is evaluated, both acceleration check 1 and acceleration check 2 are evaluated. Actually, that's too much. We only need one of those two checks, namely check 1 if the velocity is below 10 and check 2 otherwise. This unnecessary computation cannot be eliminated by the pacing type refinement because the information which check is actually needed is not available statically. Our second optimization, the filter refinement transformation, addresses this by inserting a filter condition. This filter condition is evaluated dynamically and ensures that the actual stream is only computed when needed by the trigger condition. This means that acceleration check 1 is only extended when the velocity is below 10, and check 2 is only extended when this is not the case. There's also some technical modifications to the trigger condition that are needed to ensure that the result of the trigger is not affected by this change, but I'm not going to go into this detail now. Now, in our experiments, we have, of course, tried the pacing type and the filter refinements. We have also added further code optimizations that are known from standard programming languages. Sparse conditional constant propagation inlines constant streams and then simplifies the resulting expressions. It also does a simple form of that code elimination. That means it removes streams that are never accessed. Common subexpression elimination identifies, just as the name suggests, common subexpressions and avoids duplicated computations by introducing new streams for these subexpressions. The data that I will show you are from geofencing specifications. This is a somewhat more complicated class of specifications than our running example. What we do here is we check that the aircraft stays in an area which is described as a polygon. This is, of course, a very important monitoring task. For example, we're concerned that a drone should not get too close to an airport. We work with randomly generated events, allowing also for random gaps in the data, and each monitoring is carried out multiple times so that we have a bit of statistical data to play with. In the first experiment, we use only constant propagation. So that eliminates a fair number of streams and, most importantly, results in a twofold speedup. Not bad. Now, the second experiment is about pacing type refinement. So here we add a number of type annotations for geofence with 5 faces, that's 32 type annotations. And we get a really impressive 3-fold speedup. Now, in the next experiment, we have a little bit of a shock. So we tried filter refinement both alone and in combination with common sub-expression refinement. Now, the result is actually a slowdown, and a pretty bad one, a 3-fold slowdown. So what's wrong here? Well, our original specification had absolutely no filter conditions, and apparently the introduction of the filter conditions caused so much work that the total effect of the transformation became negative. Now, to test this theory, we also tried filter refinement on specifications that already had filter conditions. And here the picture is completely different. Filter refinement is not as powerful as pacing type refinement, but still delivers an approximately 30% speed up. And this is absolutely to be expected since filter refinement is a dynamic technique. So to conclude, we are actually quite pleased with these results. These automatic transformations help the developer to focus on having readable and maintainable specifications without sacrificing efficiency. We found that classic compiler optimizations like constant propagation also work for monitoring, but really the most encouraging results come from using specialized optimizations like pacing type refinement. What we plan to do for future work is we'll look into more optimizations, obviously, and in heuristics that figure out when to best use them. The filter refinement that actually can do harm is, of course, a strong motivation for this. Another interesting question is how the different optimizations play together. It seems that some complement each other nicely. We saw that, for example, with the filter refinement and the common sub-expression elimination. And others actually seem to undo some of each other's work. An example of this is constant propagation, which inlines code, and common sub-expression elimination, which again factors out such code. So the combination of such optimization requires some attention. Well, thank you very much for your attention, and I'm looking forward to your questions.
Thank you very much for this interesting talk. The floor is open for questions. Okay, let me maybe start by one, and in the meantime, maybe some other questions pop up. So my first question would be with respect to the events that you filter out. So how complete is that? Or can you just give us an example on other types of events that are not necessary for the triggers, but still remain in the streams?
Okay, I mean, there is no semantic analysis going on, right? So the pacing type refinement is simply based on the pacing type. So it propagates the pacing type through the Lola specification, and the filter refinement propagates the filter. But of course, a semantic analysis could, for example, predetermine the value of an if condition and then throw out more code, right? So there's definitely room for further optimizations.
And how does the approach behave when you have pacing expressions that include disjunction, not only conjunctions, right? Can it propagate it in the same way, or are you just aiming for conjunctive filtering options?
No, I mean, the pacing type can be an arbitrary Boolean expression, right? That means that reasoning about pacing type is actually NP hard, but fortunately the pacing types aren't that complicated, so this is not much of an issue.
All right, thank you. Any other questions from the audience?
Maybe I can ask a question, so I'm not allowed to raise the hand as the co-host, so I'm jumping in. Do you see any optimizations that would be inspired really by the monitoring problems and that could influence and contribute to the optimizations in the programming languages? So to have this kind of the other way around inspiration.
By the monitoring problem, you mean that it's specific to the monitoring language rather than a generic programming optimization? Yeah. So I mean, actually, we played with that, right? So the constant propagation, for example, is a classic programming optimization that you would also find in a compiler. And here, the advantage to do it on an intermediate representation is mainly that it applies uniformly to interpreted monitoring or to compiled monitoring or to some static analysis that you might be doing. But then the pacing type and the filter refinement, they actually change the streams that are being computed by the monitor. So this is something that wouldn't make much sense in a program. This is something that is motivated by the fact that you don't care about these intermediate values. It's only the value of the trigger that matters in the end. So this is highly specific for monitoring. And
but do you see what my question was, that some of these highly specific optimizations could still somehow inspire some more general optimizations in the program, in the more general programming languages?
Oh, you mean the other way around? If this could inspire for yeah, I mean, I could definitely see that. I mean, there is a strong connection between languages like Lola for monitoring and then synchronous programming languages, right, like STRL and so forth. And what we're doing here could have an impact on that as well, right? Because actually, this is also a stream processing kind of framework. So similar optimizations should apply there.
Actually,
and
probably in any kind of data flow languages.
Exactly, yes. And some of these things are being done there. But I actually think the concept of a trigger makes quite a bit of a difference.
All right. So if there are no other questions, thank you all again for the nice presentations. The Slack channel is of course open. If there are any follow-up questions, please go ahead and type your questions there. And thank you all for attending. See you soon. Bye-bye.
Thank you, Hazen. Bye.
Bye.